Hello, hi, and voila, come back to the magic book. Michio Kaku's Quantum Supremacy. I began reading it this morning, and I learned about the Copenhagen interpretation and the Everett interpretation. I had partiality to Hugh Everett because he was a graduate student in physics. You know, anybody, being been there, done that kind of a thing here. So yeah, the Copenhagen interpretation deals with the fact that waves, quantum particles, you know, as waves, there's of course, I looked up the internet. There's the wave particle, same old hat, wave particle duality theory, and complementary. They're both of them are complementary to each other. The waves and the particles, the properties of light and other quantum particles. So the process of collapsing the wave seems so alien, so contrived and artificial. Yet it is the crucial process that allows one to leave the quantum world and enter our macroscopic world. So, looking at a beach, it's the wrong time of the year in Toronto, but those on the West Coast can go to a beach. You see waves, and I even observe them, counting them, and there's no definite pattern. Sometimes there's six fading out, collapsing, 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 and coming out of the beach as four. So the waves receding or receding waves in English is receding wave. So six, sometimes seven. I thought a seven would be really neat, continuous seven, seven octaves, seven colors, and seven. So that would be really neat. But there's no definite pattern. Sometimes it's just fine. You have a huge wave coming, then slowly, slowly, slowly. So this is the Copenhagen interpretation. All right, and on a quantum level, the electrons in the water molecule, they are all moving as waves. And looking up the internet, as I said, I couldn't find the actual paper, the Heisenberg answer paper, which deals with the measurement of of this collapsing wave. I think I'm also not sure, because the reference I looked up, I thought I would combine with a German Canadian professor I know, Professor Zanstra. He's in UBC now, and send an email to the journal asking if he can translate. Professor Zanstra can translate, so I can actually make the right calculations, because there's probability density involved. And if you look at it, all right, this is chocolate macaron. I was making French toast this morning, and it was a perfect example to show waves, because it's a more liquidy baking batter. All right, so here, look here. So waves, waves. So you have concentric circles, and and on a quantum level, you have all these particles. There's coconut flour, so it's probably starch. So the starch electrons, and so they're all mixing, and I can say on a macroscopic level that the wave, depending on how I move my hand, can be measured. The wave can be measured. It's a cyclic wave, right? So per second, maybe, one cycle per second. So on a if I were to measure the momentum, so the momentum would be, of course, angular momentum, angular momentum. Per unit time, so that would be change in momentum, but angular momentum per unit time would be change in momentum. So again, we would go to angular acceleration or something. But so this on a for a quantum particle, so it's mixing. So you cannot, Heisenberg's uncertainty principle. Everybody knows this. There's no, you cannot definitely pinpoint the position and momentum of a quantum particle when it's moving around. So the momentum of each quantum particle would be perhaps described by the probability density function. So that was the clue given on the internet. And really, Niels Bohr and Werner Heisenberg are in me at this time. All right. So there's so I have to look up. I have not been taught probability density function, but I have a surprise for you. Um, Calculus. Calculus would be good. So I'll go to the. I'll come to that. Before that, or I'll do a deal with the calculus particle. As or this may be good. So this is of course particles, mixed palette, particles of paint. All right, all merging together. And so the wave particle duality theory. So those were the waves in the coconut macaroon mixture. And this the recipe comes from the back here. And you need to add a little milk, otherwise it's not right. It's too stiff. All right, so you can drop spoonfuls. Maybe it's all going to crumble. And these are particles. So I'm going to make a rainbow here quickly. And so there's violet. Mix violet. Violet is oil because I didn't have violet in. So indigo. I make do with pink or purple. Purple may be better. Purple, indigo. So this is oil again. So violet, indigo, maybe purple and pink mixed together. I bought these to represent Monet's colors. So mixing together, you see in concentric waves, the particles mixing together. And just a rainbow, right? So nothing fancy. It's not a painting class. Blue, acrylic again. Um, with green, it's a special green. It's more like a fresh wind, spring green, green with or yellow. Orange red. So I'm going to make a rainbow, which means that spring's going to come soon. It's cold all month. And I'll have to position the computer this way. Or I think I have a wide angle camera lens. All right, this is all right. Mixing the colors together, where I'll just get the violet done. And mixing Monet's colors together, indigo. The indigo, there's a little bit of indigo. And then blue. So these are particles, and the particles are making waves out of the particles in a wavy motion. So the light um, falling on these colors is, I think, going to, be the wave. I guess, right? So these are particles. These are. Okay. So maybe mix it all up. or on one side. I think it's, so how soon do we see the color? It's so with the wavelength of the blue light. So these are all questions. I'll let your teachers enjoy, professors and teachers enjoy themselves. All right. So that was part one. So part two, I promised you a mathematics portion. So new. So this is what's been given. So the operator A on the eigenvalue and the eigenvectors. So operator on the position and momentum. So the Copenhagen interpretation. So the waves collapsing, etc. So that multiplied by the um, eigenvector operator matrix gives rise to the eigenvalue, eigenfunction multiplied by the eigenvector. So I've taken eigenvector as an identity vector. All right, identity vector. So now um, particle. So psi 1, psi 2, momentum del psi 1 by del t, del psi 2 by del t. So that's going back to the classical physics definition by Newton. So this, and then of course, you multiply these two, and you get is equal to actually, characteristic equation. So I would have to take the determinant, and a determinant is easy. You have to set the determinant to zero. So that is so it leads to this, and I have made some notes here, and so this is a basic. So the constants of integration is the difference between the limits in each case. So it would be time. So let's say 0 to uh, you know because I would be integrating with respect to time here, right? Integrating with respect to time. So 6 minutes, waves continuously. If I were to mix this whole um, macaroon, chocolate macaroon batter, then it would be, uh, so the difference between limits cancel out, because there are, constants of integration on both sides. So on both sides, so they cancel out, and so nowhere am I integrating with respect to psi. Psi is the wave function, right? Wave function. So phi would be the particle. So this would be here. It's all particle. So my own equation for this is del square psi by del t square plus del psi by del t plus psi is equal to a constant or a zero. So I need the paper. I need to tell this German journal. I need the original Niels Bohr, Werner Heisenberg paper, and I need to plot through the probability density function and figure out the math for this. All right, because classical mechanics collapses, but there's some calculus coming in here, which could make matters easier. So phi, if I were to look at phi, particles of paint mixing together in wave-like motion, but then, so the duality, the particle and wave duality, properties, duality, complementarity, both of them complement each other. So at times they're particles, at times they're waves. They behave as waves because you cannot think of an electron behaving as a wave. It's a particle, but it behaves as waves. So as you see, I mean, mixing this chocolate macaron pate, you see them on a macroscopic level. It's functioning as waves, circular waves. So looking at the phi, so del squares phi by del t square plus del phi by del t plus phi again is equal to a constant or a zero. So those are, I need the paper. So I will definitely at some point in time have a part two for this, but I need the German translation for the paper. maybe if I were to, there are textbooks, but the link does not lead to a whole lot of explanation, because otherwise nobody would buy the textbook, right? So this is sciencedirect.com. So Science Direct shows excerpts from a textbook and says you need to buy. So at this time, I think I led you into the interesting world of engineering physics. All right, signing out, Gayatri VC. Thank you.